My name is Andrew Saxe, and I'm going to tell you about our work on the neural race reduction. This is joint work with Shagun Sodhani and Sam Lewallen. Shagun's at FAIR and Sam is at UCL. So the power of deep networks is their ability to learn nonlinear representations. And somehow this depends on their architecture. We all have the intuition that if you set up the architecture correctly to resonate with the task, that you'll learn appropriate representations for that task that generalize well. We sought to develop a theoretical framework that would start to illuminate some of the interplay between architecture, representation learning, and generalization. Our framework builds on a gated deep linear network. You can take a neural network and schematize it as an architecture graph with nodes and edges and hidden activity vectors and weights as usual. And in this network, we'll just allow signals to flow linearly, except for one twist, which is these gating variables. These are scalars that control the pathways of information flow in the network and allow it to do nonlinear computation. You can think of it as a relaxation of ReLU, where you write the ReLU as a step function times a linear function, and that step function is the gating variable. We analyze gradient descent in this model, and it turns out that gradient descent can be written in a simple way. If you're interested in the gradient through one edge, turns out it will depend on paths that flow through that edge. And what we can do is enumerate all of those paths, and we get a gradient expression that depends strikingly only on very specific statistics of your data set. The intuition is that each pathway behaves like a deep linear network. Gating controls the effective data set for each pathway. And if an edge participates in many pathways, it will learn faster. So we can solve these different deep linear network problems and stitch them together to get the full solution for the nonlinear network. Let's see how this works in the XOR problem. For solving the XOR problem with this network, you can pull out one neuron, plot its weights as a vector back to the input, and it will be on in one half space and off in another half space. And so from its perspective, its effective data set is just these top two examples. Another neuron will have another effective data set, and we can solve all of these different effective data set dynamics and stitch them together to get the full solution. So if you train just a standard ReLU network, PyTorch as usual, we'll have this loss trajectory and it learns a particular hidden representation. And we can predict this analytically using the gated deep linear network. There's a question, however, which is there are lots of gating structures that you could use to get zero training error in a large network. Which one will a network actually use? And this brings us to the idea of the neural race reduction. The idea is in a very large network, you have many different gating schemes at initialization. And so these yield different effective data sets and different deep linear network trajectories. And we can just solve all of those, enumerate them, find which ones learn the fastest, and those will dominate the solution. So to see how this works in an interesting setting, we have this routing network, which you can think of as multilingual translation, trying to translate between French and German and Spanish and so on. And if you enumerate pathways through this network, you'll see that the shared hidden layer participates in more pathways than the input or output specific pathways. And that means that the shared hidden layer will learn more, and it also turns out it learns an abstract representation. Using this, we can describe its loss trajectory. We can also describe the details of its internal representation and how that changes. And one consequence is systematic generalization. So even when you don't train this network on all input-output domain pairs, it can still generalize across unseen domain pairs just by switching the gating. So to summarize, gated deep linear networks are a simple surrogate model for studying aspects of nonlinear representation learning, architecture, and generalization, deep in the feature learning enriched regime. The dynamics take the form of a neural race with different pathways viewing different effective data sets, and winning pathways dominate the solution. For more, you can check out our paper, which has simulations in richer settings to show that qualitatively similar results hold. Thanks for your attention.